Hey Audioholics, I'm Matthew Pose, and today we're going to be talking about Room EQ Wizard. This is a basic intro video that'll help you get started in taking your first measurements. If you're already experienced in taking measurements, this may be an enjoyable video, but it may not be all that helpful for you. Room EQ Wizard, REW or REW, is a free software that allows you to take measurements of your system in your room. This is really helpful. If you're new to home theater or audio, this allows you to integrate bass very well, as well as troubleshoot problems you may be having. In addition, if you are new to this and you're having trouble figuring out what's going on with your system, and you've joined some of our forums, you'll know that one of the first things we often say to you is, do you know how to take measurements? Now, this may be an overwhelming question at first, and that's the whole purpose of this video. By teaching you how to use REW, you'll be able to start taking measurements, and you can send us those files, and we'll be able to do a better job helping you. In order to get started, you're going to need a measurement microphone. This is the Dayton Audio UMM6 USB measurement microphone, and it's one of the cheapest and easiest ways to get started. This measurement microphone connects through a USB port on the bottom into your laptop. You change a few sound settings, and you're ready to go. This microphone costs less than $100, which makes it a very cheap and easy way to get into this. In order to take measurements, we're going to need to connect an HDMI cable between our laptop and our receiver. Here I'm going to take this end of the HDMI cable and I'm going to plug it into the side of my laptop like this. I take the other end of the HDMI cable and I plug it into my receiver. At this point I'm ready to take measurements. It's important that we do this because we need to be able to send sound signals from the laptop to the receiver in order to take measurements. In order to take measurements, we're going to want to take more than one measurement in the room. I usually start by taking a single measurement in the central listening position. Here you can see I have the mic roughly in the middle where my head would be. I would take my first measurement here, and then I would move the mic to the side of where my head is. So here you can see I've moved the mic over, I would take another measurement, and then I would slide the mic to the other side, take another measurement. Now 3 is probably a good number to get started, but you may want to consider taking more measurements by raising it up or lowering it down.
So now I'm going to show you how to take measurements. The first thing we need to do is click on Preferences, and the reason is we need to make sure we have sound set up correctly. I'm using the Java settings because compared to ASIO it's more foolproof, it's easier when you're getting started. You'll see that I've set this up to be connected to my Onkyo receiver. You can see the left and right channels there that are being selected. It's saying one is the channel it would play back on, one is the timing reference. The microphone that I have selected is the USB microphone that I'm using, and you can see I've already loaded a calibration file. Now, I've done this before, so I have that all loaded. For you, you'd have to put the file on your computer and load it up. So now I'm starting to take a measurement. You can see that I've set the range that I'm going to do already. So 10 Hertz to 20 kilohertz or 22 kilohertz is fine. And then you run a measurement. So here, there's going to be a sweep in a moment. Here comes the sweep. And I've intentionally kept some of the sound of that sweep in the video because I wanted to make it so that if you've never done this before, we actually have seen this on forums where people will say they've taken measurements, they don't look right to us, and we're saying, are you hearing a sweep? And we find out there was no sweep, it wasn't connected correctly. So what's just appeared is a steady state response with no smoothing, so it probably looks terrible. So I've applied some smoothing to this. You know, you can do 1/6, 1/12, 1/24, 1/48. At a certain point, you're not applying enough smoothing to be useful, and so I've just done this to make it easier to see what's going on generally, but you may want to try something that's a little bit coarser, so like 1/12 or 1/24. It's just that you start to see things that aren't really audible. So I'm doing another sweep. What am I doing? Well, I'm taking a measurement of the left speaker, I'm taking a measurement of the right speaker. That's because I'm doing full frequency response measurements. When you're setting up subwoofers, you still should be doing full frequency response measurements, and the reason is because you want to see how everything's integrating. Yeah, you could go to 500 Hertz, but I think why not just go to 20 kilohertz and get everything. And then what you do is you move the mic. So you remember earlier I was showing you I take microphone measurements at different positions within the listening area. So what I'm going to do is take a left and a right measurement in the central listening area to make sure that the left and right channels look basically the same. And then I'm going to add in some other measurements at different measurement points. And you can do the left and the right again. One reason to do this is you may want to make sure that each of the seats is getting the same optimal sound. The center seat in my system is dead center between the speakers, so the left and right speakers are symmetric. But as you move to either side, that's not true anymore. One speaker is farther away than the other to the listener. So taking left and right separate measurements can help you to identify if there's any anomalies going on. So again, here you see another sweep coming in. One of the things that I'm not doing as good a job of here that you'll want to do, but you will see that I did do this in the first two, is label those. So you'll want to make sure you're carefully labeling them, like left 1, left 2, or it might be like left measurement 1, left measurement 2. That's so you don't lose track of what these measurements are. It's also helpful if you're going to share these measurements on the forums with us so that we can help aid in troubleshooting. That way we know what your measurements were. So I'm using really quick, simple measurements just to make this easier for myself. So I'm taking another sweep, and you basically keep doing this. Now, if you're just getting started, I think 3 measurements is probably okay. If you are wanting to be more adventurous, really getting closer to 6 measurements is probably better. And the reason is because getting 3 around the head of where you sit is fine. But you may also want to get measurements in the seat next to you, because maybe that's a commonly used seat that you want to make sure is good. Or what I often do, even if I'm just optimizing for one listening position, is I also raise the mic up a little bit higher than the head and down a little bit lower. And there's a couple reasons for that. One is you have to remember that this is an omnidirectional microphone. And omnidirectional microphones pick up sound differently than our ears do. On top of that, the analysis software that we're using, this FFT software, doesn't work the way our brain does. So basically 2 directional ears with binaural sound detection tied to a very smart brain basically is able to do things with the sound that a computer and a single omnidirectional measurement can't do. So we want to take a bunch of measurements because we want to try to get a sense of what the ear is actually hearing. To do that, that's why I take, like I said, a bunch of different measurements, because I start to get a better sense of what's happening. And you'll notice that each of the measurements is not identical. So in this past measurement I just took, there was a big trough, a big dip in the response. And that dip was basically infinitely deep. It was caused by a cancellation from a room mode, basically a reflection off one of the walls. You can't EQ that. You would have to treat that in some way, and it's low enough in frequency it would be fairly difficult to treat. So probably the better solution would not be necessarily treating it, but actually trying to address it through things like placement of the subwoofers, placement of the speakers. You may move your listening position around if possible, or to be honest, it wasn't all that wide, so you might ignore it and it may not be all that audible. What you probably wouldn't do is EQ it. So here you can see that we've overlaid all of the measurements that I've taken so far. And you can see that they're very smooth and the scale is fairly wide. I did this earlier on purpose just to make it easier to look at, but actually this isn't really useful if you're trying to figure out what are the problems in the low frequencies. So at Audioholics, the preference is generally to remove smoothing when looking at low frequencies and to use roughly a 50 decibel range. So what I'm doing now is I'm changing this. And you can see I accidentally put in -40, which is why it looks even smoother than it did before, so I'm going to change that now to 40. And now you can see this is going between 40 and 90 decibels. And now those anomalies in the response are a bit more obvious. The lines are representing 5 decibels, so we can start to see that the response here has variation that is in the neighborhood of plus or minus 5 decibels or more. But we're still seeing that it's very smooth, and especially below 50 Hertz, there's nothing going on. So I'm going to go over to the settings here, and I'm going to actually I'm going to remove all the smoothing that I applied earlier. Now you can see that the response is a bit more anomalous. You can see some of the variations in the response, even down below 50 Hertz. There's some variation that we didn't notice before, and especially what you can see are those cancellation dips, and you can see that they seem to go on almost forever. In fact, if you look at them, whereas the response is typically in the neighborhood of around 75 to 78 decibels, those dips are down around 30-35 decibels. And so those cancellation dips would be examples of areas where we wouldn't want to make corrections. One of the interesting things is that while you see this very extreme dip at 120 Hertz in all of the different measurement positions, you'll notice that there's other places, like around 78 Hertz it looks like, where there's a dip in that green line, but there is no dip that really matches that in the other measurements. In fact, we see peaks in most of the other measurements. Only that blue measurement line shows a dip that is in a somewhat similar position, although that one is centered more at 70 Hertz. And so this is a good example of why you want to take a bunch of measurements in order to see what's really going on and apply EQ appropriately. So here I'm starting to show you what it looks like as I go through the measurements. If you look at the levels down in the bottom there, you can see that they're hovering all around 73, 74, 75 decibels or so. It looks like one of them is a little bit higher. but up around 80 decibels. But that green line down at that dip was somewhere around 35 decibels, so quite a bit lower than the other measurements. You can also see that the response extends below 20 Hertz, and then there's a big dip. I'm not actually highlighting this at the moment, but if you look, there's a big dip around 12 Hertz. That dip is sort of an artifact of the way the measurements were taken in my room and the way the speakers themselves interact. It's correctable, but my view is that at frequencies that low, who cares? Now here I'm going to increase the frequency range up to 500 Hertz. And so what I wanted to show here was actually that you'll start to see that these cancellation dips seem to be happening more and more often and closer together. That's because at lower frequencies, below what's known as the Schroeder frequency or FS of the room, we tend to see very widely spaced modes, which cause these dips to happen, but that you can see big spaces between them. And at a certain point, you hit what's kind of known as the unimodal region of the room. It's the place where typically the longest dimension, the length of the room, is really dominating. So at this point I'm going to start taking some more measurements. We already took a bunch of measurements in different measurement positions, but I want to take some more measurements around the seating area just to see if I can find any more variation in the low frequencies, and use that information to help make judgments about the acoustics of the room, as well as some considerations around how I might EQ the system. Now, one of the things I've done is I've gone ahead and I've added a timing reference to this. So here you can just see the measurement was taken, was captured. It's sweeping through. The high frequency blip you heard at the beginning was the acoustic timing reference that I was using. The reason you use an acoustic timing reference is that when you're using a USB microphone and an HDMI output, it's the only kind of timing reference that you can use. The loopback timing reference wouldn't work in that scenario since there's different clocks in the USB microphone and in the HDMI device, and so this allows you to still retain some timing information and allow you to look at the differences in the timing of different speakers.
So here I'm going to show one of the neat features that Room EQ has, which is a tool for simulating basically room modes and SBIR effects. So room modes are what happens when sound waves bounce off of boundaries in the room, and then as they pass by you, the listener, interfere with the sound waves coming either from other reflections in the room or the speaker itself. At low frequencies, most of what you hear involves reflections around the room, which is why you'll often hear people like myself and others at Audioholics saying that the sound of bass in a room is actually the sound of the room and not the sound of the speaker or subwoofer itself. It's because what you hear is not the direct sound from the speaker, but that's direct sound from the speaker having bounced around the room. As it interferes, it causes these peaks and dips, which are called destructive and constructive interference. Now, something similar happens with SBIR effects. SBIR effects are when the sound waves pass by the speaker itself, so they bounce off of a boundary in the room, and then as they pass by the speaker, they constructively or destructively interfere. Now, one of the things you see me doing here is I'm actually turning off a couple of the mode types. I'm turning off the what they're called the highest order modes. So low order modes are axial, length, width, and height modes, and some of the what are called, maybe we'll call them sort of mid-level tangential modes, but I turned off the oblique modes and some of the higher order tangential modes because they don't tend to be as obvious in the room, their effect, and they tend to be a little bit higher in the bass frequencies. What we're really interested here is the effects of the speaker placement and number of subwoofers on the bass response quality, and so it's those lower order modes that are most important. Now, what I'm doing right now is adjusting the placement of the microphone. This is a simulation, but it's simulating what would happen if you had microphones at those particular positions. And what you'll see as I add in the microphones is that these tend to match up where different listening positions would be. Now, I've set this up so that we can see the most amount of variance that you would see in a room, again, based on what might be typical listening positions. You may say, hey, you know what, I don't care about my spouse or my kids or anybody else who comes and listens. I really care about what I hear. That's what's most important. So I want to know that the bass is flat where I listen.
You can place those microphones closer, but you still should be both simulating and measuring a variety of measurement positions, because a microphone doesn't detect sound in a room the same way our ears do, and the software we use to process it doesn't process it the same way that our brain does. And as a result, what happens is that we start to see things in our measurements that are not a perfect approximation of what we hear, and we can overinterpret that. So by taking multiple measurements, we can actually get a more accurate sense of what's going on. Now, a lot of people do also want to make sure that the sound is as good as possible across a range of listening positions, and so you would want to simulate and again measure that spatial variance that you see across all the listening positions, as I've done here in the simulator. Through the use of multiple subwoofers, which I'm going to be showing you in a moment, you can actually reduce variance quite a bit over a very large listening area. Now, at the moment, what you're seeing me do is test out what it would look like in a typical system with a left and a right speaker, no crossovers of any kind, a single subwoofer. I'm showing you what happens when you make the main speakers sealed versus ported. It matters, but actually the main point I want to make to you is that some people have this belief that if you have ported speakers and sealed subs, or sealed speakers and ported subs, they somehow don't blend well in the room. There are differences in how they interact with each other and the room, and it can complicate things a little bit, but it certainly is not true to say that you can't use a mix of sealed and ported. You can even use a mix of sealed and ported subwoofers, and everything can be blended and integrated fine. Now, in this case, what I'm showing you is what happens when you move a subwoofer around the room. You can see that this single subwoofer, this single low frequency source, mixed with the left and right speaker, which themselves are also low frequency sources, changes what modes are being activated. And that's important because that gets at the notion that where you place the subwoofer affects the response. You can also see that while it mattered, it didn't make as big a variance as, for instance, now adding in a second subwoofer. And one of the things to keep in mind is that adding multiple subwoofers, the goal of that is to reduce variance. You may actually see a worse response with multiple subwoofers without any EQ. It would depend on the room itself, the number of subwoofers, their placement, things like that, but given that EQing low frequencies works so well, it's not something to be concerned with. What you really want to focus on is how big a difference there are between the different microphone positions. And here I've added a third sub. I think what you can see pretty clearly is that as I add in this extra sub, while some things have gotten a little bit worse, overall it seems like variance is reduced, especially in this particular case above 60 Hertz. There's some stuff going on below 60 Hertz that kind of needs to be addressed still, and this is pretty common. Unfortunately, the hardest stuff to deal with tends to be what's going on above 50 or 60 Hertz, and we only typically operate our subwoofers up to about 80 or 100 Hertz, meaning that even though multiple low frequency sources does help to reduce variance between listening positions, we don't really use multiple low frequency sources up that high. So I'm showing this to you just so you can see what happens, but as I mentioned, there's the most modes up above 50 or 60 Hertz, and we don't actually use multiple subwoofers there. The best way to fix above that range is actually careful placement and then a well-treated room. And I'll just say, as somebody who provides these services, I don't personally believe that a well-treated room has to use commercially available acoustic treatments. The furniture in the room, curtains, carpet, all sorts of different things can be used to treat a room, bookshelves, you name it. Obviously, in a studio or in a place where you want the best possible sound and you're trying to make sure that you know what's going to happen, you would want to use commercial products or products you've built to a certain standard in order to assure that you get the response and the effect that you want. But for the average listener, how the room looks and how livable it is as important as anything else. Now, you've been seeing me play around with all the features while I'm talking to you about various unrelated things, and what I'm trying to show you is what happens when you place the subwoofers in different locations. At the moment, what you see me doing is clicking on and off the inverting of certain subwoofers so that you can see how inverting specific subwoofers affects the response. So in this particular location, it makes quite a bit of sense actually to invert relative to the other subwoofers, those which are in the back of the room, or in this case I actually inverted one on the side and one in the back. And so the bigger point here is not to go with what you see going on in the simulator, but that you may want to play around with that. Something I didn't mention earlier that I'll mention now though, is that the simulator is not perfectly accurate, so it's a nice tool to play around with that helps you to get a sense of what happens when you place the subwoofers in particular locations in a room of particular dimensions and with particular amounts of absorption. The problem is, it's assuming that the walls themselves are rigid, it's assuming that the absorption coefficient is fixed at all frequencies, and it's assuming that the room is a perfect cuboid. So, for the most part, because of furniture
and closets and you name it, rooms are not perfect cuboids. They do not have perfectly rigid walls. In fact, short of a steel bunker, they would never have rigid walls. And we know that the absorption is not flat. So walls themselves actually have a resonance frequency that they absorb at, and the Q and dampening of that resonant frequency depends on the wall's construction. And so even though most walls are constructed in the same way and it tends to be pretty similar, you know, in a basement you actually have usually a foundation. And so the foundation is very, very rigid. And on the other side of that foundation is dirt, which it's very well damped. Inside your room, you would have a normally constructed wall, but it's sitting, let's say, 4 to 6 inches in front of that foundation wall. And in a lot of theaters, it's gotten popular to use constrained layer dampening, which is something like green glue, multiple layers of drywall, and they sit on something that actually articulates the wall. So it's an isolated mount and then a steel hat channel. So that actually provides a great deal of dampening and changes the resonant frequency of the wall. So even though it provides soundproofing, it also actually turns the wall into a bass trap. It always absorbs some bass, but it actually increases the amount of bass absorption. So you can see I'm continuing to play around with the features. This is, again, the specifics are less important because it's going to depend on your room and subwoofers and speaker placement. In practice, you're going to find that the simulator doesn't really match what you're getting perfectly, but it does show you what happens when you adjust all these parameters. And so it can show you how important it is to individually delay the subwoofers, that even when they're perfectly aligned with each other from the standpoint of the impulse response, that the response itself may not be as flat as it could be, which is why you'll often see in the simulation, but also in my own setup work, that I might invert some of the subwoofers to help. All of this is because each of the low frequency sources, those main speakers, which are a low frequency source, and the subwoofers, are all stimulating different modes in the room. They're activating them. And they kind of work together to help create an overall smoother response that's easier to EQ. But sometimes the way that you get the best response for that involves, as I said, inverting some of them, changing the delay, changing the level. There are softwares out there, like the multi-sub optimizer, that can actually mathematically simulate what's going on in a room. And by doing that, they can give an accurate set of instructions on how to set the EQ, the delay, and the gain on each sub for the flattest possible response, but you can also play around with it as I am here manually. So you can see these little variations. What I've done now, by the way, is turned off all the other measurement positions because it's easier to see what's going on when you look at just one measurement position on the effect. So now I've turned on a crossover, and the point here is to show you what happens when you add a crossover. I've changed it to 80 Hertz. You can see now that the main speakers are no longer operating as low frequency sources down past 45 Hertz, that there is this point just below where the speakers fall off that seems to be causing some change in the response by adding in the crossover. I don't personally like to add a high pass filter on my mains. I like to operate my mains full range. And the advantage of that is that they are able to then contribute as a low frequency source. There's some sound quality advantages as well. By using the main speakers as low frequency sources, they also technically constitute a stereo left and right low frequency source. And so for recordings which do have what might be called stereo bass, it helps to improve spaciousness. So you don't hear that as like a left and a right bass. Below actually about 150 Hertz or so, you don't tend to hear direction of bass all that much, but you do hear what's referred to as spatial variation, spatial differences in the bass position. And so this work, which was really pushed by David Greisinger from Lexicon, helps us to get a better sense of how realistic, like doing this gives us a more realistic sound. And so I like to use the front, left, and right speakers because they contribute importantly to the overall realistic nature of that sound that we hear, and they reduce spatial variation. They improve the sound quality itself by reducing the amplitude variance. Now here I'm showing what happens when you seal the room versus not. You can see that by sealing the room, the lowest frequencies are enhanced a bit. Most rooms are not truly sealed, but if you have a room, especially one that's like a soundproof room that's been built with very tight construction and very solid doors, it might perform more like a sealed room, especially if it's in a basement with those really, really solid, rigid concrete walls, versus upstairs where, or a main floor where the wall construction is such that it wouldn't probably act like a true sealed room. Here you can see that moving the subwoofer around in placement like this changes the cancellation effects, and that these cancellation effects don't really match modes all that often, only sometimes. And that's because what you're seeing is a mixture of modal effects and SBIR effects. So the SBIR effects, again, that's when the sound waves coming from the speaker actually pass. So what they do is they bounce off a wall and then they pass by the speaker and they constructively or destructively interfere. So that's why it's so important to make sure that the subwoofers and the main speakers are placed critically, because they have the biggest effect on the response above 50 Hertz, and you can't really fix it with multiple subwoofers or EQ because it'll vary by your listening position. And so what you end up having to do instead is making sure that your placement is optimized. You can use acoustic treatments to help, but adding a ton of absorption to a room is not only not practical, it's not always the best way to get the best sound. So here you can see what happens when I start to add subwoofers back in. We start to see that the response flattens out a little bit. So this is the impulse response of the system, and what I've done is I've actually done what's called overlays, which allows me to look at the impulse from all the different systems. I've changed the view now so it's easier to look at. That initial peak is the direct sound, and then what you see is after the initial peak, all these little peaks and dips are reflections in the response. So you can see I'm plotting it normalized, some settings so you can see how this works, but the idea is that this shows us how the system works.
So here we're going to go ahead and look at the steady state response. We're going to be doing some analysis of the room based on all those measurements. This is just one of the measurement positions, but you can do this with all of them. So the steady state response refers to the general frequency response of the system. Now the next thing we're going to look at is delay. So this is the decay rate of the room. I shouldn't say delay, it's the decay rate of the room. So this is RT60. And what I've done here is I've already set this up so that you can look at two of the numbers which I think are the most reasonable to look at. The TOPT is a form of RT60 that's a little bit more accurate, and EDT. Now keep in mind that in a small room, this is not the most valid. You don't want to go to an acoustics book and look up RT60 and follow those instructions because they don't make sense. But this is an objective measurement of decay in the room. And so typically you want to look and make sure it's flat, relatively smooth. Acoustic treatments are typically the way to address this. Now this is a waterfall plot. I'm not a huge fan of waterfall plots, and I want to point something out. Because this is a minimum phase system, basically all of the response issues, now I'm turning off cumulative spectral decay CSD mode. It doesn't make sense to use that when you're looking at an in-room response. That might make sense if you were doing a direct speaker response anechoically or in free space. Now notice all of the peaks and dips in the response correlate with troughs and ridges in the decay. In any minimum phase system, that will always be true. And at low frequencies, the system, even in a room, will always be minimum phase. So what you can see is, outside of some noise, so when you get into the lower stuff here, what you're really seeing is just some noise. For the most part, all those peaks and dips are simply a reflection of modes. So I have a big mode in my room at around 22 Hertz. It's a length mode. And if you look at my system, you'll see there's a little bit of a peak at around 22 Hertz, and there's some ringing at 22 Hertz. That's normal. That's what happens when you have a little bit of ringing. And if we were to reduce that, for instance, with some EQ, or it would take a huge bass trap, but if we had a bass trap to get rid of that, you would see that that actually would largely go away. So here I am going back and forth between the steady state response and the waterfall to make that point that when you see a peak or a dip, you will see that as a trough or a ridge in the waterfall. Now, why are waterfalls useful? As I mentioned, I don't use them a lot. I'm not a huge fan of them, but the reason why they can be useful is when you're trying to specifically zero in on the exact point at which you need to apply EQ. That can be helpful. It's also kind of a neat way once you do apply EQ to see the effect that it does have in this time domain. So here I'm just aligning, as you can see, the cursor with a peak in the response, which I showed earlier. And you can see that they match each other. You can see that there are troughs on either side. I'm going back now to this one that's around 21, 22 Hertz. And if you were to measure with a tape measure in my room and calculate what the length mode should be, it's practically on the nose with where that ridge is. And you can see there's a little bit of a boost in the response down low. Now there's another one below 20 Hertz. I don't really know what that is. It's not likely to be a mode. Now here I've gone to a distortion plot. For the most part, in-room distortion plots are not super useful other than when you're trying to troubleshoot. So the reason is that the room itself affects the distortion quite a bit, and it can go both ways, because you can get all sorts of weird noises in a room that can actually increase distortion, and at the same time you can get usually a reduction in distortion at low frequencies because of room gain. So this isn't like an accurate scientific measure of distortion, but it can be helpful to look at distortion just to see if something's wrong. Sometimes people have broken speakers and they can't tell what's going on. Distortion plot shows that. So here we're looking at the waterfall again, and I'm looking down and at below 20 Hertz to see what's going on here. As I said, this is kind of odd. So some of the things I sometimes look at is there evidence in the noise floor that this is actually just noise in the room? And that happens sometimes. The waterfalls tend to be sensitive to picking up in the decay stuff that's actually just noise. It's one of the things that can be confusing when looking at these and trying to figure out what's going on, is you'll sometimes see this garbage at the bottom, and you'll think that there's something wrong with your speaker system, that it's you know, that it's got some sort of ringing going on, and in fact it's not ringing, it's really just noise. So here I'm looking at the level of the noise floor, and what I can see is that the noise floor still seems to be below where I saw the level of the waterfall plot. So it doesn't look like it's noise. It still might be noise of some kind. I mean, the other thing it can be is it may not be what's being shown as the noise floor of the room, but it may have been some sort of a hum that was in the room that that wasn't noticed. It's below 20 Hertz. It's not audible. It could even be an artifact in the measurement. Who knows? It doesn't correspond with any sort of peak in the response, so it's unlikely to be anything meaningful. Now, this is a wavelet. Now, the nice thing about wavelets is that essentially a wavelet like this is the same thing as a waterfall plot. Now, it's not just displayed differently. Some people think that, but a wavelet actually is different than an FFT, which is the way all the rest of these measurements were done. Now, don't worry about what that means. What it really means in practice is that you're able to have a high level of resolution in both the frequency and the time domain, which is not true of the waterfall. So you'll notice here, in looking at this, even though I've applied some smoothing to it to make it easier to read, that there's quite a bit of detail. And I can go in and I can adjust the smoothing and see even more detail if I really want to. So what I'm doing is I'm adjusting the scale to make it useful. Now that black line refers to the peak energy in the system. So think of it this way. At time 0, that's when the speaker starts playing, and energy comes out of the speakers, and what this is showing us is that at low frequencies where my subwoofers are, the peak energy is happening later than the peak energy of the main system at, as I mentioned, time 0. Now you might say, oh, so your subwoofers are delayed. Yes, probably there is some delay in the system that's causing this, but it's relatively minor. Most of this is that as you get to the bottom of the range of a speaker, where there's a natural acoustic high pass, or if you apply a high pass filter to them using crossovers, what happens is that you naturally get an increase in group delay, and that increase causes this increase in delay as well. So here I'm going down lower in frequency because as we hit the point that's the natural low frequency limit of my subwoofers, we're seeing that in fact, yes, the peak energy does increase dramatically. Overall, like it's farther out in time. It actually becomes huge. It's just a big red blob, basically. So just to wrap up, we're going to go ahead and talk about what we've learned. So basically we've learned how to use REW, and it's really pretty easy to use. You just have to get used to how to set it up and which buttons to be pushing. It helps with acoustic analysis, so you can get a sense of what's going on in your room, and if there's some trouble areas, what to do about it. And I think most importantly, it helps to optimize the low frequency response. So this tends to be the reason most people go to REW. Setting up subwoofers can be tricky, and this is really a great aid in helping to do that well. So I hope this was helpful.